All right. Hello, everyone. We're going to get started. Oh, yeah. So we're now on day 4 of the 2539 programming workshop. Here we are on the timeline. So today we are going to be learning about Path Planner and Autonomous. So for those that are new to FRC, Autonomous period is the first 15 seconds of every game. And in these first 15 seconds, you have to, the robot has to complete tasks on its own. So there is no driver input and everything has to be pre-programmed onto the robot. And usually autonomous points are weighted higher than teleop points. So it is a very important part of the game to get good at. And they're also sometimes tiebreakers. So we're going to be focusing on autonomous. All right. There are multiple kinds of autonomous control. So here are the 3 major types of autonomous control. We have the time-based control. This one is just setting your motors to drive for a certain amount of time and guessing how much time will get you to a certain area of the field. And this is prone to error, but it is simple to implement. However, it does make it harder to make more complex paths as you have to guess more numbers and more times. And again, the errors can keep on compounding. PID-based control, which we'll be going over a little bit, drives the motors to specific distances. And it uses PID controllers for that. It uses the sensors like the gyro, and it's more reliable because it uses the PID control. This requires larger commands and can be used for more complex paths. Something that we'll be focusing more on in this session is Path Planner. And this application lets you follow more complex trajectories by default. You can actually just draw on the path and the robot will be able to calculate your trajectory and go on that path. It uses all the sensors that are available on your robot, and it can be as accurate as PID. And you may have heard of other path optimizers out there like Choreo, and Path Planner works in conjunction with Choreo as well. All right, so here is a pretty simple time-based control example for autonomous. So over here, you can see that the motor is set to drive with a timeout. You set just a certain drive percent on the motors and it will time out at 0.5 seconds. So this robot will only drive for 0.5 seconds and then it will drive for 0.25 seconds at a new speed. So here's our approach to turning with PID. So instead of using the time-based control, we can be using PID to make more accurate turns instead of just guessing the amount of time it takes to get somewhere. So the first step in doing this is storing the desired angle somewhere in the code. And then you want to be using your PID controller and a minimum speed to turn the direction, the robot in the direction of the angle that you've stored. And this is with feedback from the gyro. And then the third step is finishing when the angle is within tolerance. So once your angle of the robot that the robot is sending back to you is within the tolerance that you have set, it will finish that command. Here's how to set up a gyro. It's a simple gyro setup. This is, I believe, for the NavX, which is what we are going to be using on our robot here. So over here, you're just setting the gyro to a new attitude and heading reference system. That's the class. And then you're going to be resetting the gyro so that the gyro isn't tainted by your prior runs. All right. So here is our PID-based control example. Here we are attempting to turn to an angle. So in order to turn to an angle, we have to set up a PID controller that is going to control our angle. And we're setting our desired angle, like we said in the previous slide. So here we are converting our angle into radians. So you want to be careful about your units because sometimes that can cause some issues. So at 2539, we always use radians, and I believe that is the standard for most teams. And here we are setting our tolerance to 0.1 degrees, which is again set to radians. Is there any questions about this right now? Oh, and for those of you who have just joined, this presentation will be linked somewhere in the chat. If someone can get that in the chat, that'd be great. All right. Continuing on our PID-based control example, here, this is the initialize. So we are setting the set point in our angle PID controller to the desired angle. And while it's executing, all it's doing is the PID controller is calculating how much it will need to turn in order to get to that desired angle that is within the tolerance. And once the robot knows that it's at the set point, it returns true to the is finished and it will stop. All right, if you want to drive straight using PID, you have to approach both sides of the robot, especially if you're in tank drive separately. So you have to store the distance relative to each side of the robot. And then you have to drive each side to their respective distances using PID and the minimum speed. And again, you have to finish when both of them are within a given tolerance, like the previous example. Any questions on that? All right. Oh, so this is a simple motor feed forward. Here we have, we've talked about feed forward in the PID section of day 3, if you recall. So some of the components here are KS. If you've taken a physics course, you know that static friction is a thing. So when you're trying to move your robot, you have to overcome the static friction of the ground. And we add a feed forward KS, just a constant. The K just means a constant, in order to overcome that static friction. And it makes the work on the PID controller a little bit easier. KV is for your desired velocity, the voltage for that. And then optional, we use KA for your desired acceleration times KA, and that's the voltage. All right. So a PID-based forward example is here. So here you can see that we're setting 2 different PID controllers because we have to control the left side of the robot and the right side of the robot. Here we have the left, here's the right, and these are just our constants for the PID controller. We set the desired distance like we did for the angle and the targets. And we also set our tolerances here. All right, so here the PID controller is telling the robot how much further it needs to get to reach that desired distance, and it's getting there. And we're also resetting each controller so that it's not tainted by anything you have done previously. And the set point is set to where you need to go, which is the desired distance. All right, so for the execute, here the PID controller for each side of the robot is calculating how much the robot needs to go. And it's adding that minimum speed so that even if it has to only go a little bit forward, it will still be going at that minimal speed that we have set to that desired distance. And then again, once we are finished, if the left controller and the right controller is at the set point that we have determined previously, the autonomous function will finish. Any questions? Okay, moving on to Path Planner. So what is Path Planner and why do we use it? So Path Planner is an application and a tool that we use in FRC to help simplify our auto building process in a way that we can still make complex autos in a way that makes more sense to us as humans. It's a very visual system. So here's the application for Path Planner. I believe if you don't have Path Planner installed, we can also send a link to that in the chat. It's a fairly easy installation process. So to create a trajectory with Path Planner, there is a very helpful GUI that they have, and all you have to do is drag and drop the waypoints that they call it. They call them waypoints to the specific X and Y coordinates that you want your robot to go to, and then you also have to set your heading, and it will generate a path or a trajectory using whatever you have input into the GUI. There are also functions at the bottom of Path Planner that make it really easy to see what your path is going to look like when you're going to be running it. So there is a play function. So you can, once you're done creating your path, you can see exactly where the robot is going, making sure it doesn't run into anything, and making sure that your path is actually what you want it to do. There are also a lot of other features on Path Planner that I urge you to explore. The Path Planner docs are a great place to start. All right. Okay, so there are two components of Path Planner code that we will be going over. So the odometry, and this uses the gyro encoders on the motors to track on the field. So the motors only really know, or the encoders only really know how to run. However, we need to convert that into where positionally on that field. So we need to track distance these motors have gone and relate that to their field position using odometry. And then we have the auto builder, and this is a section of the code that will generate the command that will follow the path that is generated by Path Planner. All right. So this is an example of odometry in the drive subsystem. So this will be under your drive subsystem file in your code, in your robot code. Over here, you can see that we have a few accessor methods that are just getting the pose in meters and the rotation. And here we are just resetting the odometry again, so it isn't tainted by previous runs. Oh, and here for the odometry, this line over here, basically all it is doing is it's creating a differential drive odometry that will a new post TD that will show where the robot is on the field, and the kinematics is where, or the motion of the robot instead of relative to the motors, relative to where the robot is moving on the field. Okay, over here, all it is doing is getting the distances for both sides of the robot, so both of the motors, and converting it from how many rotations or like how far the motor has turned to how far the motor has actually moved the robot. So this is just the math for that. And over here, it's doing the same thing, but for the velocity of the robot. And then it's updating the odometry and the pose. We need to be setting robot constants to measure the distance that the robot travels, and these are stored in the drive.java file. Are there any questions about the odometry? All right, I'm not seeing any questions. So we can move on to the auto builder. So the auto builder is in the robot container. Oh, this is not the right file. Sorry, guys. Let me just Yeah, this is hidden for some reason. Actually, it might be in like version history. All right, we got the slide back. So this is the example that we showed prior is an outdated auto builder. This is the way that you should be doing it now. And this is from the Path Planner docs. So this auto builder is in the robot container. And basically all it is doing is that it's sending a sendable chooser. It's sending a chooser to the smart dashboard. And smart dashboard makes it very easy to choose the autos in a way that's like, again, it only is one line of code here. And they have a built-in auto builder. So it's very easy to create like a very simple auto builder and send it to your dashboard. And Smart Dashboard can be replaced with Shuffleboard or whichever dashboard that you are using. All right, that was pretty quick, but our lab is pretty extensive today, so I'll be handing it off to Matthew for the lab after a quick break.
Okay, guys, we're back for the lab. This is Matthew Malunik returning with the lab section. And so basically for our lab, it is pretty big today. We're going to first kind of go through all the different auto types that we went over today, starting with time-based autos, right? Just turning to an angle and then driving forwards a certain distance, both solely based on time. We're going to upgrade that to PID-based autos, where we turn to a specific angle using PID and a gyro, and then we're also going to drive forward using the odometry from our wheels. This is going to require a gyroscope of some sort. We're going to be using NavX for our case, and it's also going to require, motors that have odometry or encoders on them. So, for example, we're using Neo 550s. They have built-in encoders, so that is not going to be an issue for us. But if you're using brushed motors, your motors would need to have an added encoder. And finally, we're going to be using Path Planner, which kind of takes that PID-based auto, odometry-based, gyro-based aiming and stuff, and takes that to the next level with that GUI. So going into our programming workshop, right, our robot directory. First, what we're going to want to do is kind of just go into robot container. The time-based autos are very, very simple, right? Pretty much what we're going to do is we're just going to create a sequential command that runs a drive command with a timeout. So for the drive commands we have, this is kind of what one of those drive commands would look like right here. To make this a little easier on ourselves, we're going to make a new method in the drive subsystem that creates a drive command that just runs at a certain speed. Sorry, I did not actually enter the drive subsystem there. So down here, we're going to create a new command, public command, oops, caps lock, public command, and then drive at speed command. And we're going to have our double, and let's do left speed and our right speed. Now, this is going to be a lot like this method up here for set speeds, but it's going to be in command form. So instead of a method you need to constantly call, we're just going to return it as a command, which we can run. So we're going to make use of the run method. So run, and then our arrow function syntax. And then we're going to do set speeds and just left speed, right speed. And also, we're going to make sure that we return this. So if we go back into robot container, if you guys have that down. You good? Okay. We're going to create a command specifically with an S dot sequence. And this is just a static method that takes a list of commands, as many as you want. And what it does is it runs the first one, it runs the second one, it runs the third one, and it just keeps on going until they're all over. And it does them in order. So only one is running at a time. So what we want to do, since our goal for this time-based auto is to turn and then drive forwards, our first command is going to be drive subsystem. So m underscore drive subsystem dot, and then drive at speeds command. And since we want to turn, we want our one side to be going forwards while the other side is going backwards. Then we can add another command from the drive subsystem dot drive at speeds command. And we're just going to go full speed forwards. For the case of this demonstration, I'm actually going to lower those a bit to 0.25, just so we don't crash the robot into anyone. More specifically for the driving, because the turning, you're less likely to hit someone, but just in case. And we're going to set, basically this, if we were to run this right now, it would actually just go on forever. It would never stop turning because we don't have a timeout yet. So this command here right now runs forever, but we can make it stop after a certain time with the dot with timeout method that we talked about last time. So we're going to have it turn for 1 second, just a second, and then we're going to have it drive forwards for also just 1 second. So this whole auto should be 2 seconds. In your actual autonomous period, you have 15 seconds. So this is clearly not a full autonomous, but it's a good example. Any questions? In that case, we are going to be deploying this to the robot and attempting to run it in autonomous. So hopefully that works. So we did successfully deploy that robot code. So we're going to take a sneak peek at the robot down here. And we're going to try running. So first I'm going to move it to a bit safer of a location. So I'm going to move it here. And also, since this is autonomous, it's very important to say enabling, because usually if you enable IntelliOp, for the most part, you're going to know that your robot's probably not going to move. But in autonomous, your robot's definitely going to move. If you're doing it right, your robot probably should move. And there's a lot higher of a chance that if you make a mistake, it's going to move the opposite direction you think. There's a lot higher of a chance it's going to hit someone. So you definitely want to say enabling as loud as you can. And also, when you enable, make sure you have your finger on the enter key of your keyboard. If you press that, it stops the robot. So that's for safety. Auto server. Also, yes, when your auto finishes, end it anyway. Just because. So we're going to be enabling an autonomous in 3, 2, 1. So as you can see, it turned around and then it drove and did each of those for a second. Something else you can see is that the turn wasn't very centered. That's kind of part of the doing it by timeout. It wasn't very precise, and neither was the driving forwards or backwards. Just for fun, we can do that again, but after we have these students walk by. Enabling. So as you can see, the robot successfully turns around and drives. So our time-based autos were successful. You can see these are very simple. If you're kind of struggling to understand the rest of these ideas, or after today you're still struggling, but you really need an auto that just like moves, time-based autos are a great option because they're very simple to create. One downside is you do kind of just need to trial and error with the times until it does what you want. And it's still not going to be very consistent, even when you do find the right times. So next we're going to be doing these PID-based autos. And again, just the same simple auto is pretty much what we're going to be doing. The turn to an angle, specifically, I think we're going to be doing turn 180 degrees around and then drive forwards. And for this one, we're going to be driving forwards a certain distance. Now, well, you could do this in a method kind of like this. The easiest way to do it is actually by making actual like physical command class. So we have our aim April tag command and follow April tag commands from last time. If you don't have them, basically what they do is they use a PID controller to specifically the aim at April tag uses a PID controller to turn the robot so that based on limelight input, an April tag is centered. We're going to end up doing something really similar to this for our turning using our gyro. First, though, before we create these commands, we're going to need to add a few pretty useful things. Firstly, we need to have a gyro, right? Our robot is using a NavX provided by Kawaii Labs, or I think that's about how you pronounce the name. But that library is not included in WPILib by default, so it is a vendor library. We're going to need to install it. So if we go online, okay, that didn't open up any windows. Online. Any second now. There we go. And we look up WPILib third-party libraries. Should be the first result. And you can just scroll on down until you find Kawaii Labs or I think that's how it's pronounced. Libraries for Navex, blah, 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 blah. And you're going to want to do this link. It's below the name. It's not the one above it. It's the one below it. And I will post that in the chat for you guys. So you want to copy that, go into VS Code, manage vendor libraries, install new libraries online, and then you're going to want to just paste that in and press enter. It appears we have had a slight issue with a network timeout. So I'm just going to try that again and hope. Let me just make sure I don't already have this installed. Okay, I'm going to close my VS Code and then open it up again and see if that fixes the issue. But I'll work through this temporary pause for now until we figure that out. If you have any questions, leave them in the chat. Okay, so that time it was successful. Clearly just a quirk of probably having VS Code been left open for about a week. Says it's recommended to run a build after a vendor update to ensure dependencies are installed correctly. You're just going to want to press yes. 1 second. Sorry about that pounding noise in the background. If you can hear it, we're not quite sure what it is. Maybe someone's using a hammer upstairs, but right now it is building. And so once that builds, we'll be able to create our gyro, specifically our Navex gyro. So our build was successful, and so we're going to want to create a new Navex right here. Now the class for Navex, kind of counterintuitively, is AHRS, I think, perhaps. Maybe I'm misspelling that. My apologies, guys.
I don't care.
Yeah, I'm just gonna try installing this library too, but so it appears it just took a little bit of time to show up, but AHRS from quilabs.navex tab, and that should import it from quilabs.navex.frc. If it's not showing up for you for some reason, maybe import this too. You really shouldn't need to, but I just did it and it showed up, probably due to coincidence. But maybe that is the trick. Probably not though. So anyway, AHRS M gyro equals, and then you're gonna want to do new AHRS, and then SPI dot port dot I think that's almost right. One second. We're gonna check WPIlib right now because my autocorrect is kind of malfunctioning right now. But if you look up gyro WPIlib and then gyroscope software, if we scroll down to navex, spi.port.kmxp. So you're going to want to use that as your port, not that. spi.port.kxmp. Okay, so the trick is you need to press tab after port. So you need to tab when you're typing port. Otherwise, it doesn't show up properly because it's not imported. So we have our gyro. Sorry that took so long. I've had slight technical issues. And we have created it on the port. That is basically the default port for the RoboRio. If you have your Navex kind of just like planted on top of your RoboRio like most teams do. Now we're going to want to make a method to basically get the angle that our robot is at, and we want to make that slightly more accessible. So we're going to put a method down here. Let's call it public, and then get rotation, or get gyro. And we're going to need a return type of rotation 2D. Now, rotation 2D is basically just a wrapper type for an angle. It gives you a lot of nice methods you can use with angles. So you can get it as a degree form, as a radian form, or in rotations if you want. That way you don't have to be too worried about sending the right value over. So we're just going to return new rotation 2D, or actually you can do rotation 2D dot from rotations, and then gyro dot get angle. Now, if we look at the signature for this method, we see that it's actually in degrees, not rotations. So we're going to want to change this from rotations to from degrees. So this is going to be our method to get the angle of the robot. Now, this is going to give you the angle of the robot relative to which direction it was facing when it turned on. Something that you're going to find with that is you might want to tell the robot what angle it's at, because for some reason you might not be starting perfectly straight. In a lot of autos this year, for example, you might start on the subwoofer, you start at an angle. You would want to be able to tell the robot somehow you're starting at an angle and it's not 0. So to do that, we can make another method called set gyro. And this will take a rotation 2D as a parameter. And all we're going to do is do m gyro dot set reset. So it appears this one only has a reset gyro option, which sets the yaw to be 0. Some gyroscopes do have other options for this, but this one appears to only have a reset. So we're just going to rename this one to reset gyro. So we have our gyro set up now. Next, we need to set up our odometry. So odometry wise, we're going to do differential drive and then odometry. And we're going to call this odometry. And it's going to be equal to a new differential drive odometry. And you're going to have a lot of options. This one specifically works pretty well. So we're going to start with a rotation from our gyro of 0. If you just create a rotation 2D like that, it pretty much does, it just sets it to 0. We're going to want to get the position of the encoders on our wheels, which should all be 0. And we're going to want to get the pose that we're starting at, which can just be a new pose 2D. Just making sure to import everything. Since this is a bit long, it does make sense to move this from the top here actually into our constructor for the subsystem. Additionally, we're going to kind of in advance want to add a differential drive kinematics. And make sure we import that. I want more robot. Defined like that. And then down here at the bottom, we're going to do m kinematics equals new differential drive kinematics. And all that you submit for the kinematics is how far apart the two sides of your robot are. In our case, it's about 30 inches. 30 inches in meters, though, as the distance is in meters for this. To convert inches to meters, something you can do is use the units library. You just type units, tab, and then dot, and then we're going to do inches to meters. And we're going to put down 30. So we have our odometer created and we have our kinematics created. Now we need still about 2 more things. We need to be able to get the encoder values for our left side and our right side. And basically your encoder value is just how far that side has traveled overall. It's like your car has an odometer in it. That's basically how far your car has traveled. We want to see how far has the left side traveled in net, how far has the right side traveled in net. So public void, not void actually, double, and then get right encoder position, return. And for this robot, at least, we're going to go with the not follow motors, the lead motors. So motor front left, or I guess in this case, motor front right. And then get encoder. And then get position. And then we're also going to want to do that for the right side. Sorry, for the left side. So one thing to know about this returns your motor rotations, right? And while rotations are useful, they're not actually how far your robot's going to travel, right? Like you wouldn't say, I walked 20 rotations forwards. That kind of doesn't mean anything. What it can help us find is through some calculations how far a robot's actually going to travel. So robots, their motors are usually hooked up to a gearbox, which is then hooked up to a wheel, right? Your gearbox is going to have a gear ratio, usually a reduction. So your motor will say spin 10 times for every 1 time your wheel ends up rotating. On our robot, this is allegedly 10.71. So we're going to divide both of these by 10.71. And then the radius of our wheels, I believe, is about 8 inches, give or take. So again here, this is in inches, and we want this output to be in meters, so we're going to need to use the units library to convert it to meters. So units dot inches to meters. And then we're going to want the same thing down here. Something that would be very helpful to do right now is to look at this number and see, okay, look, this is repeated. Look at this number, say, okay, this is repeated. And also look at this number up here and be like, okay, maybe it's not quite repeated, but it is a number that we would like to be able to easily change in case, say, our robot changed sizes. Now, usually robots don't magically change sizes, but maybe CAD comes in and they remove the middle of your robot and now it's like 3 inches wide, right? Maybe you don't want to have to look around for this number. So we can actually save it as a final a constant at the top of our drive subsystem to make it a little easier to change that if we ever need to. So we can do final, double, and then we're going to call this one our track width meters. And then it's just going to be equal to this. So units dot inches to meters, 30. And we're also going to copy those other two up. So right here where we took it out, we're going to replace it with track width meters. Our gear ratio is this, so we're going to copy that out and bring it up to the top. And then just the gear ratio should be fine for that one. And then finally for our wheel diameter, we're going to copy this one out. And we're going to put in final double wheel diameter meters. Now, one benefit of this is it makes this code a little bit easier to read, but also if we end up using these values somewhere else, we're only going to ever have to modify them in one spot. So for the PID-based turning, these methods in specific are going to be the important ones for us to know. To do PID-based turning, you need to create a command. So we're going to do turn to angle command .java, like that. And we're going to create a constructor for it. Just like that as well. We're going to want to make sure that it extends command, because this is a command. And that allows us to kind of make use of all the pre-built things for commands that there are. Also, we're going to want to make sure that it takes as a requirement the drive subsystem. That way, we're actually able to like drive and stuff. And we also just want to save that drive subsystem as a parameter, not a parameter, as a field. Now, in addition to the drive subsystem as a parameter, we're also going to want to take a parameter, which is basically how much we're going to turn, right? So in this case, I think it would make sense to turn a certain amount relative to where we started. So we're going to take that as a rotation 2D and then turn amount. And we're going to save that. We can also probably make this one private, double, or actually rotation, turn amount equals nothing there. But down here, turn amount equals turn amount. That's pretty much going to be the setup for this turning command.
Yeah, I do. And I looked at.
Next, we're going to create an initialize method. And this is going to run, of course, at the start of our command. Since we want to turn a certain amount relative to where we already are, we need to know where we're starting at, right? And the way we're going to do that is double starting angle equals drive subsystem, and then get gyro. So this is where we're starting, and this should actually be a rotation 2D. My bad. To get our final angle, we just want to add the starting angle with the turn amount. And we're going to get final angle equals starting angle dot plus, and then turn amount. Now we're getting an error here because we still haven't created this field up here, but we're going to want to create another rotation 2D field, and we're going to call it final angle. Next, in our execute statement, we're going to want to turn the robot based on our PID, which we still haven't actually created. So up here, we're going to want a private PID controller, and we're going to call this MPID controller. And we're going to want to make sure that's imported. And we're going to set this to a new PID controller. The values that we used for last time's PID controller were pretty good, a little slow though, so I'm going to bump them up slightly with 0.05, 0, and then 0. Now, this was also in degrees, now that I think about it. So we can multiply it by 360 and then divide by pi, or 2 pi, because we're going to be feeding this in radians. Or we could just feed it in degrees, actually, now that I think about it, since we're using rotations. So we're going to leave that as that is. Now, when we initialize, actually, back up here again. Sorry. Our PID controller, we still want to set the tolerance. And that is going to be, since we're going in degrees, 3 degrees is probably good. And we also want to add the drive subsystem as a requirement. So in our initialization, we know our final angle that we're going to. So we want to set our set point to that angle. And we're also going to want to get this in degrees. Now in execute, we should finally be able to get this turning done. We're going to want to take the drive subsystem, and we already have our set arcade speeds command. Or not command, method. We're going to use that one because it makes turning pretty easy. Our forward speed is going to be 0, and our turning speed is going to be calculated based off of the PID. So we're going to make a new double. We're going to call it calculated turning speed. And we're going to take our PID controller and calculate and we're going to use the current gyro angle. So m drive subsystem dot get gyro. And we're also going to get this one in degrees too. And we're just going to pass it in there. So this here should, for the most part, do that calculation of how much we need to be turning. Now, for ending, public void end, we take our parameter of whether or not the command was interrupted, and we're really just going to tell the robot to stop once we reach our desired position. And we're just going to do that by setting arcade speeds with both of them equal to 0. Now, we need some way for this command to actually end, and we're going to do that with public void is not void, boolean is finished. And that is going to return a boolean. And we're going to see that by using mpid controller dot at set point. So that should be the finished command. If you guys have any questions, now's a good time to ask about this before we move on to the driving distance based on PID. In that case, we're going to move on to driving distance based on PID. So just to make it a little simpler, we're going to duplicate this and rename it to drive to distance. So also, we're just going to make sure that is renamed drive to distance. And also this. Instead of taking a turn amount, since this is a driving command, we're going to take a double as a distance. And because we're controlling both sides, we're going to want to include a PID controller for both of the sides. So private PID controller. And we're going to make this one right and this one left. We're also going to save our driving distance amount like we did last time. And we're going to add a little m there just for clarity. And we're also going to rename this to distance. For our left PID controller, we're just going to go with these numbers for now. There's a possibility that this is going to drive a little slow. Actually, there's a very high possibility this is going to drive a little slow. We're going to go with 1 for now, which basically means if we're supposed to be going 1 meter away, we should be going at full speed. This feels right given the units. And then for our right PID controller, we're going to want to use the same PID values. And also same tolerance for both of them. Honestly, our tolerance should not be 3 meters. It should probably be a lot less. For the case of this, I'm going to go with 5 centimeters. And we're going to keep our one requirement of the drive subsystem. So this is the completed constructor for our drive to distance command. When initializing, we're going to want to find our final position for each side. And we're also going to want to base that off of where we're starting and the amount of distance we've gone. This is a pretty verbose way of writing that out to make it clear, but you can also do it inline to kind of save space and not declare as many variables. So I'm going to do that here. MPID controller left, and then set point. And we're going to do drive subsystem get left encoder position, and then just plus distance amount. And then we're going to do the same thing for the right side. So MPID controller right dot set point. Then M drive subsystem dot get right encoder position plus M distance amount. And that basically tells our robot you want to drive this far into the forward direction by distance amount. For execute, we're going to be using a calculated driving speed, and we're going not to be using set arcade speeds, but set speeds, just plain set speeds, because we're going to be controlling each side individually. And I'm just going to remove that real quick. Similar to what we did up here, instead of making a variable for each calculated speed, we can just calculate it directly. So MPID controller left dot calculate, and then we're going to do drive subsystem dot get left encoder position, and that's all right. Then we're just going to do the same thing, but with the right side. And I'm just copying that there because really, you only need to change 2 words. And then I'm just going to move that comma so it's in a little more natural of a position. And that should be your execute. Our end is still fine because we're basically just telling the robot to stop. And our is finished. This one only checks if one PID controller is at a satisfied state. We want to check if both of our PID controllers are at a satisfied state. So we're going to do M PID controller left at set point, and then we're going to use this AND symbol, which basically takes 2 booleans, one on the left, one on the right, returns true if both of them are true. And we're going to do M PID controller right dot at set point. So this command should basically run until it reaches the correct distance. I'm just removing rotation 2D up at the top there because we don't actually use one of this, so it's an unused import. Does anyone have any questions about that command? Okay, so now that we have those properly created commands, we're going to go back into our robot container, right? We have this sequence, time-based. We're just going to comment it out. And we're going to make a new sequence, right? So return commands dot sequence, like before, just takes as many commands as you want. In fact, you can even pass no commands if you want, right? It just does nothing. And ends instantly. But first we're going to turn. So turn to angle command. And we're going to pass in our drive subsystem. And we're going to pass in how much we want to turn. So we want to turn 180 degrees. We want to turn completely around. We're going to do rotation 2D dot from degrees 180. And we're going to make sure we tab on that rotation 2D so we end up importing it. Instead of doing from degrees 180, right, just to give an example, you could do rotation 2D dot from rotations and then 0.5. And that would literally return the same object as the from degrees one. Now, for our second command, we want to drive forwards. We're going to drive 1 meter. So new drive to distance command. We're going to pass in our drive subsystem, and then we're just going to pass in 1 because we want to drive 1 meter forwards. So theoretically, this new auto should work, and it should just turn our robot around 180 degrees much more accurately than previously and drive. So I'm going to actually drive the robot over here, and we're going to deploy that code. So our code is successfully deployed. We're going to drive our robot out before we test our auto for safety. This one doesn't even have timeouts, so if I did it wrong, it could literally just go on forever. So there's our robot out on the field, and hopefully this works. Unfortunately, it appears to not have worked. We are turning around in a circle forever. So going back to this, right? We have our PID controller. We're setting our final angle, get degrees. We're adding these two. I just want to confirm here that everything's in degrees, because if it's not in degrees, you could end up with something like that happening. So our gyro is hopefully reporting our number of degrees. Something that would probably be helpful to confirm here is that we actually are connected to our gyro. So right here in get gyro, I'm going to also have it print out the gyro angle. Now, hopefully, if our gyro is actually changing like it should be, we're going to see that number going up. And theoretically, it should be going past 180, at which point it should stop. Possibly, though, if our gyro isn't working right now for some reason or isn't connected properly in the code, that could cause an issue, and we would see that then. So the code successfully deployed. I'm going to turn the computer over this way to look. But I'm also kind of going to keep my eye on the computer. If we drive out, I'm pretty sure this is just going to spin in circles again. But I should be able to see some logging of the angle that we're flying. And it actually appears. Oh, this is one small issue I'm now realizing. The computer that deployed, which is getting the logs, is not actively connected to the robot, so it is not able to see those outputs. Luckily, we should be able to open up the logs on the driver station. And what we see, this is actually very helpful. Unfortunately, you guys can't see it, but we are getting numbers, and they are changing. They're just going down, not up. So basically, we just need to change which direction it's turning, so it turns in the correct direction. Basically, right now, it's trying to get to 180, or it thinks it's trying to get to 180, and to get to 180, it is turning the wrong direction, and so it never gets to 180. So pretty much for that, to fix that issue, in our turn to angle command, we're just going to look at execute, this calculate, and we're just going to put a negative there. And that should fix the issue. At least if that's the only issue.
Yes.
Some issues like this, you're really only going to find out either through very, very, I guess, in-depth analysis of your code and your robot construction, or you're just going to find them when you test your code. If you have the opportunity to actually test your code, usually that's going to take less time than thinking so thoroughly through your code as to whether or not it's going to turn exactly the right direction the first time. So our change successfully deployed. If we attempt again, we can see our robot. And now if we enable, and as you can see, it did turn about 180 degrees and then stop. And then it did in fact drive forwards. It was a bit swivelly though, I will say that. So perhaps our drive to distance command could use some work still. One thing that would be useful in this case is basically constantly making sure that our robot is pointed the same direction it was when the command started. So what we can do for that is kind of copy this turn to angle command, or certain parts of it, specifically this, or not this here, right? And kind of reconsider the driving based on both sides approach for that. Basically, what I think the issue in this case is that this robot's wheels are not super responsive. Specifically, one side kind of drags a bit more than the other side. It drives with a bit of an asymmetry. So just purely assuming that if you end up with the same end distance on both wheels, you're going to have equal results is not necessarily accurate. So what we can do is either take this, or just for the sake of saving my code, I'm going to create a copy of this one. And I'm just going to rename the first. I'm going to rename this one. I'm just going to name that one 2 for now. But we're just going to deal with the first one. We can firstly change this to a distance PID controller, and this one to an angle PID controller. So one way to do that across the whole file at once is just change this one to distance, and then this one to angle. We're going to go with the PID controller that we used for the previous one, the turn 180 degrees of 0.05. I might actually lower it slightly for this one because it doesn't really need to have as snappy of a motion. And for the angle, really, we're not going to worry too much about the tolerance, but we're just going to set it to 3 degrees. Now, for setting the set point for the angle, we're just going to get the gyro that we start at, right? Our starting angle, and we're going to get it in degrees. Now, for executing, we're going to change this one to set arcade speeds. And we're going to change this calculate to using the gyro. And getting degrees again. And also, since we no longer care about the angle primarily, we just kind of care about that general distance, we're going to use that. And also right here, we're just going to use the average of the two. So we're going to add them together. And we're going to divide it by 2. And we can also use that to find our starting position. So basically, this is a variation on a drive command that, based on how it responded to the first one, I think might drive a little straighter. What it does is, instead of trying to make it so both sides travel the same amount, is it tries to keep the robot straight using the gyro, and then it just makes sure that the average distance they've driven is the distance you want. So we're gonna drive the robot over here, try deploying this and seeing if it makes a difference. So we've deployed our code, and now hopefully if we test this out, it should drive a little straighter. So enabling. So enabling. And unfortunately, it appears that we forgot to invert our turning value again. So we're going to add that in right now. Drive the robot back over here and attempt that again. And then as long as we get similar results, we're going to be moving on to Path Planner, because that is a lot more commonly used today. So we deployed the code, and we're going to try one last time. So enabling. And maybe you guys couldn't quite see it, but it did drive a lot straighter that time, significantly. So I guess for a robot like this, where maybe each side isn't as close as you'd hope, using a angle-based method for driving straight does yield a significant improvement there. And I'm also sure that by tuning the PIDs for either of those, you would be able to get much better results either way. So next, we're going to move on to Path Planner. So Path Planner is kind of the final stage, or basically for tank robots at least, the final stage of a lot of autos for most teams. You're gonna find a difficult time finding a need to kind of go past Path Planner. So one of the main issues with the way we've been making autos so far is it's not graphical, right? Like this, you can kind of understand what it does, but you can't really see where the robot is on the field. you'd need to like chart it out on like a piece of paper and like measure your distances and then plug it in and then run it and see if it goes to the right spots. And that's kind of difficult. And also, who has paper anymore? You know, we're all digital now. So we're going to be adding Path Planner to this project. Yes, it's also a lot slower and not optimal. So for Path Planner is an application. So to install it, oh my, you're going to want to look at Path Planner. Should be, I would recommend going to the second link here, Path Planner GUI. Getting started, and then installing, and you're going to probably find the easiest way to install it on the Microsoft Store or the App Store, or if you use Linux or don't like getting automatic updates, you can use the manual installer. So that's another option for you. So after you install that, if you end up opening up the app, it should look like this. And you're probably going to want to click on project, not project browser, switch project. And you're going to want to choose the project that is today's project. So Programming Workshop 2024 as your project, open project. And hopefully you should see nothing except maybe this example path. This is kind of the base starting setup for Path Planner. What we're going to do is we're going to create an auto right now, just a really simple auto. Well, you start with a path, so we can use the example path. But you take this, right? Now we're going to notice this is in Swerve. Quickly head out here, go into settings, and turn off holonomic mode, right? So holonomic mode is just a fancy way of saying your robot can go forwards, backwards, turn, and go left to right at the same time. So swerve, mecanum, those would be holonomic mode. We're tank, we're not holonomic. And you can include some attributes about your robot size. This is useful because you can see it physically out on the field when you're plotting your paths. And you can choose a max velocity you want to go at and max acceleration, other limits like that. We're going to close that. We're going to open this back up. And as you can see, now we have again our beautiful paths. And this time, this rotation at the start means nothing, but our robot will follow the path we choose. So we can make a super fancy path. Right now, I'm just going to do a little circle. So I'm going to go like this. Let's say we're starting kind of in the middle of the field. I'm going to put this over here, and I'm going to drag this little tail around like that. So basically, it does an oval kind of. And I'll make it a little bigger, but that's your half semicircle. Now you're going to want to add another waypoint to your path. And the way you do that is you press waypoints over here, new waypoint after, or I guess this is a new waypoint in the middle. But we can kind of just move that over there. Sometimes this UI does take a while to get used to, so don't feel bad if you're kind of just getting a hold of it. Practice will help. And we're going to make a circle there. It's a bit squished, but I think for our purposes, it should be fine. And that's your whole auto. Basically, you just go around in a circle. Now, we want to run an auto with this, so we're going to go into new auto, which we created using the plus sign. And we're going to add a path to it. So follow path, path name, example path. And as you're going to note, the starting position is all the way down here. It starts where that starting position is, and then it tries to follow the path. Just move it to the path. That way you don't have that like giant motion occurring. So now we have both of those. We have our example path and new auto. And if you connect to your project using the switch project menu, it should have automatically saved already. If we go back in here, we should see in somewhere it is putting those paths. I can only hope. But it can't be in build. Anyway, you're also going to want to, after installing Path Planner, install Path Planner lib. So if you go to Path Planner, go down Path Planner lib, getting started. And you're going to want to copy that. I'll put the link in the chat if I can reach it. And you're also going to want to install that as a vendor library. So manage vendor libraries, install new libraries online, paste. Yes, we would like to build.
Young minds.
And we're going to give it its time. That way it can successfully include the library. And we do have it there, it appears.
Absolutely. It worked, didn't it? Wait, they're not gonna be. They're gonna sit there and they're gonna live from me.
So we have our paths included. We have our auto created, but now we still need to set up all the code that kind of tells Path Planner how to drive our robot. And in all honesty, the best way to write this code is, for the most part, for a beginner team at least, or even most intermediate teams, I'd recommend. You just go up to Path Planner lib, getting started, and then you kind of just copy the code. So this is what you would use for swerve. And we're going to be using ramset differential. So just copy, and you pretty much just paste it into your drive subsystem. So we're going to paste it right here at the bottom. Paste. Boom. And we're just going to want to remove some of the boilerplate that we don't need that is causing issues. All right, there and there, I think should be good. And you're going to notice a ton of errors. Auto Builder, first you want to tab to make sure it's imported properly. We have configure ramset, and this is going to take a lot of things. So first we need to have some method to get the robot pose. We're going to need to have some method to tell the robot where it is, basically reset the pose. You'd use this at the beginning of autos. Get the current speeds. So get the current velocity of the robot pretty much. And we're going to need a method that takes in chassis speeds and drives the robot at that speed. As you can pretty much see here. This section right here is kind of done for you, as is this, so you don't really have to worry about it. So for get pose, that's kind of where this M odometry and M kinematics things are going to come in again. We didn't actually need them for the PID based autos. I kind of got a bit ahead of myself, but we are going to need them now. So what you're going to want to do is go down to periodic. We haven't used this yet, but we're going to use it now. So M odometry and then dot update. And pretty much we're going to pass in our gyro. So M gyro. Dot get rotation 2D. I guess that works. Then we're going to do our left wheel positions, I believe, are an option, and then our right wheel positions. But I would like to make sure the method does accept those. It appears it only takes differential drive wheel positions. So mgyro.getRotation, and then new differential drive wheel positions. And we're going to choose the second one there. And it's literally just asking for what is the left encoder position, what is the right encoder position. So we're just going to tell it that. Left encoder position, right encoder position. So what this M odometry update does is it kind of in the background keeps track of where the robot is based on what the gyro information was. We're going to want to make a reset position method. So public void reset position. And we're going to allow a pose 2D to be passed in there. And we're going to talk to our odometry. So M odometry and then reset position. And we're just going to pass in our gyro position. Our differential wheel positions. So new differential wheel positions, get left encoder position, get right encoder position. And maybe it would make sense to extract this here out into another method, but I believe we should only need to do it twice, so it's not quite necessary. And then pose right at the end. And that's basically going to tell the odometer, which is kind of just, again, tracking all your wheel movements to kind of give you an estimate of where you are in the field. It's going to tell it, okay, actually, we're here now. So finally, we're going to make a get pose method, returning a pose 2D. And we're going to do m odometry.getPose meters. And that will return our pose. So of these, we have get pose, we have our reset pose, and we're just going to replace this with, what did we call it? Reset position. We still need to be able to get our current speeds, and we need to be able to drive. Now, for getting our current speeds, it needs to be in the form of something called a chassis speeds. So we're just going to make a new method that returns that to make this super easy, all the way down at the bottom. Sorry if this is getting a little hard to follow with all the scrolling, but public chassis speeds, get chassis speeds. And then return new chassis speeds. And basically, for our robot, we're going to have a forward velocity we're going at. We're going to have a velocity we're going at side to side and a rotation velocity. Since this robot is tank, our rotation velocity is always going to be 0. And our forward velocity is going to be based on those two side values. We're not actually going to use the chassis speeds constructor. I was getting a little ahead of myself there. We're going to use M kinematics, right? So this differential drive kinematics, the real purpose of it is for you to be able to kind of look to your robot and say, okay, I know my left side's going this fast. I know my right side's going this fast. What does that mean in terms of how much my robot's moving forwards, how much it's turning, and how much it's moving side to side? Probably your side to side is going to be none, but forwards and rotation could be useful. So we're going to do so we're going to do M kinematics and then 2 chassis speeds, and we need the differential drive wheel speeds this time, not positions. So new differential drive wheel speeds. And we're going to need to be able to get how fast our left wheels are moving and how fast our right wheels are moving. We can do motor, front, right, dot get encoder, dot get. And this time we're going to do velocity divided by gear ratio times wheel diameter meters. It's a bit of a mouthful. And then we need to do the same thing for the left side. So I'm just going to copy that and change right to left. And just confirming, this returns RPM. So we're going to need to change this from rotations per minute, which it is right now, to rotations per second. So units, I mean, honestly, we don't even need units for that. Rotations per minute is just going to be 60 times whatever rotations per second is, because there's 60 seconds in a minute. So we can just divide by 60. And then finally, we should be able to convert that to chassis speeds. So now we have a way of getting our chassis speeds, which means this up here, our get chassis speeds, we can just do get chassis speeds. And that is almost done. Also, if you're wondering about this colon notation, that's a really fancy way of writing this dot get pose and then like that. It's pretty much just a super fancy way of doing that. So all you need to know is you just replace the little end bit with the name of the method. Now, finally, we need to be able to drive with our chassis speeds. We're incredibly close. So we're going to do public void drive from chassis speeds. And we're going to take chassis speeds as a object. And then we're going to do m kinematics dot to wheel speeds, and we're going to pass in our chassis speeds. And we're going to need to save this as a differential drive wheel speeds. So differential, actually, in this case, there's this little trick in Java. If you don't want to write out the entire type, you can do var, and it infers the type. But we're going to do var differential speeds equals that. This is in more modern versions of Java. The most modern WPILib version should definitely have it. But differential speeds, that should work fine. If you hover over it, it'll show you what type it is. This is just a nice way to avoid having to write out that very long name. And then we're going to do, finally, after all this time, set speeds, differential speeds, dot left meters per second, and differential speeds dot right meters per second. And we still have a small error right up here with our drive. We're going to change that to set, or what do we call that method? Drive from chassis speeds. And from that, we now have our auto builder configured according to Path Planner. We go back to their docs just to make sure we're not missing anything. All this looks good. We have the auto builder properly set up. And we're going to just scroll down to here, all the way down. And this is the example we gave. Basically, you use the autobuilder.build autochooser, and then smart dashboard.put data autochooser, and then autochooser and you just make your get autonomous command auto chooser.get selected. So I'm going to copy none of this actually because it's easy enough to remember. But if we go into robot container and scroll up, we have auto chooser equals auto builder dot build auto chooser. And we're going to notice this returns a sendable chooser command type. I'm just going to copy that. And we need to save this as a method. So private boop sendable chooser command auto chooser. Now, basically, these little I guess, less than and greater than signs, they are for parameterization of a type. You don't really need to know exactly what that means, but it means you can have sendable choosers of a lot of different types, and this one specifically takes commands. So we scroll all the way here, auto chooser, and then really smart dashboard. So smart dashboard is a dashboard option that is basically kind of an old option. Shuffleboard is a more modern option built off of Smart Dashboard, but it's still kind of old, Shuffleboard. But basically, if you send this over, it'll just pop up on your Smart Dashboard, your Shuffleboard, and you should be able to pick an auto from it. And then finally, if we go all the way down here, instead of returning this as our auto, we can return our auto chooser dot get selected semicolon, and that should theoretically give us working autos, hopefully. So I'm actually going to build this code before we deploy to the robot, just in case there's some error somewhere in it. I don't think there is, but that'll also give me some time to drive the robot over while it's building, so that should save some time. If you guys have any questions, or if the one remaining of you has a question, now's a good time to ask. So we also realized the robot was kind of dying there. So sorry for the delay. The battery was kind of on life support. So we replaced that. So we're just gonna deploy this code. Yeah. Okay, so my bad. I was in the wrong programming workshop 2024 project. As you can see, this one has different autos. I'm just gonna go with this auto for now. As you can see, it kind of just like does a little chicane. We're going to change our settings real quick. Where's the settings? I think it's at the bottom, possibly. So settings, turn off holonomic mode. We're just going to leave everything else as it is. And as we can see, our path, it now does a little turn. I'm going to make a new auto, speed running this, and we're going to use the example path. And we're going to start where we should start. So now if we exit this, if we look and deploy, we see this path planner. When you look and deploy, you should see this. If you don't see it, it probably means you're in the wrong folder or something, like I was. So if we deploy our robot code again, because it appears it did not work the first time, possibly because I had my path planner set up incorrectly. And it's successful. So hopefully one last time, we're going to test out this auto. Or second to last time, because I want to make sure, I want to demonstrate getting that turn 180 degrees and then drive auto working with path planner as well. Put back here, and then go into autonomous and enable. Does nothing. You can see if there's a clear reason why. I'll change this as this. Enabling. Disabling. Connected to the robot. Enabling. Disabling. How is that even possible?
I didn't see the word.
I don't know you have to phone.
Okay, so something important to do. I'm not really able to clearly demonstrate it on this without kind of turning it over. Sorry. But wish we had a better setup for doing this. on this screen, okay, you definitely can't see that screen on the right. Maybe it's a little hard, but we have our shuffleboard. We have a custom theme set up. In the left, you'll see like network tables, and then under the smart dashboard tab, kinda, you should have an auto chooser, and you can drag that out, and it'll pop up, and you can choose an auto. By default, it defaults to none. If you choose none, your robot's not going to do anything. But you can choose new auto, and we've chosen new auto now, and so that should hopefully cause the robot to do something. One last time, enabling. Whoop. And it drove towards me very quickly. So clearly moving. I'm going to drive it a little farther back so we can kind of see what it's doing. Enabling. And it appears to just be driving very fast forwards. So that's kind of unfortunate. Probably something that could be a component is that our speeds might be like our what are they called? Our speeds could be inverted. So if we do drive to distance and kind of not drive to distance, where we drive subsystem, look around, we have get pose, reset position, get chassis speeds, drive from chassis speeds. And we're also updating this. So one option is logging this data in this case. That way you can kind of see, well, where is the robot? What position does it think it's at? Yeah. For the sake of time, we're just gonna end it here. Hopefully we'll get this sorted out by the next presentation. In which case we'll kind of explain what the issue was. Yes, it's a cliffhanger, so you can come back next time. Sorry we weren't able to get it fully driving. It is kind of a complex setup process, as you can see from all this. But we're just gonna end it off for today. Sorry if this one was a bit lengthier than last time. Autos are a pretty big topic that we wanted to cover in just one day. So thank you for coming. Have a good evening and see you guys next Monday.